Hello. Hello. Good afternoon, everyone. It is my pleasure to introduce Quentin Williams. Quentin went to Princeton for his bachelor's degree and then went to Berkeley. He was one of Raymond Jeanlot's early students for his PhD, and then he continued on to Santa Cruz, where he still is now as a distinguished professor. He's also the chair of his department and the vice chancellor?
Associate Vice Chancellor.
Associate Vice Chancellor at Santa
For
Cruz.
research.
For research.
Yes.
I have it written down. I should just
Yes.
look.
Well, I could do it myself if you'd like.
Quentin's also the PI of the compressed beamline at the ALS. He has many papers in mineral physics. He's very interdisciplinary. I met him several times at CITER, where he's done a lot of interdisciplinary research with geochemists and seismologists, geodynamicists. But today he will tell us about deep planetary interiors and iron-rich liquids. Thanks.
Thanks so much for having me. So, as I was thinking about giving this talk today, I sort of thought I would belabor things that were things I've done over the last 7 or 8 years that have some new, some older, that have a relatively common theme associated with them. And I have to say, thank you, that this is actually, I think, the first talk I've given at the Geophysical Lab since I think I was a very young graduate student in 1987. So at that point in time, Ronald Reagan was in the White House, a B-movie actor. We've moved on now. 30 years later, we have a reality show host in the White House. I'm figuring that if I come back here in 30 years, we'll probably have Beyoncé in the White House. We're hoping that there's no correlation here. Okay, so what I'm going to talk about today is, first off, seismic constraints on the deep lunar interior. That's something I did a few years back with a host of seismic collaborators. And actually, as I reflect on it, actually segues nicely into rules that are associated with how the cores of small moons circulate, how they might generate magnetospheres or not. And then I'm going to close by talking about extrapolating properties of iron-rich liquids. And in particular, I'm going to focus on iron silicon-rich liquids because those have the most data available on them. And you'll see why, I hope, that a lot of data from different sources is critical for inferring the properties of alloying materials at core conditions. And the theme of the talk is actually that mineral physicists have spent a huge amount of effort looking at things like the one over the compressibility, the bulk modulus of liquids, looking at the volume of liquids as a function of pressure and temperature. But many, many things actually hinge on derivative quantities and that are very much less known for wide suites of liquids. And in particular, I'm going to focus on thermal expansion and the pressure derivative of the bulk modulus. And that those turn out to be actually critically important for inferring the dynamics and the chemistry of planetary cores. So the underpinning message here is that ultimately the mineral physics / high pressure community needs to very much focus on relatively nuanced parameters that are rather difficult to measure to figure out how cores circulate and what their bulk composition is. So I'm going to start talking about some work at the products of a really very messy and complicated accretionary process forming the moon. And so the question here is, what's the internal structure of maybe volatile enriched? And there's been a lot of work done at DTM and some at the GL on what the volatile content of the moon might be. And certainly iron depleted and impact generated object. I'm going to talk about some seismic data that was collected a long time ago but was only recently analyzed a few years back in conjunction with a bunch of array seismologists who deployed techniques that are more commonly used for oil exploration at this juncture. So there's a large sequence of, there are many lunar quakes that occur. They top out at somewhere around magnitude 5. And there were actually 4, and for 2 weeks, 5 seismometers that were deployed on the moon during the Apollo missions. And if you look at the locations right here in red dots on the right, you'll notice that this is not how you would optimally design a seismic array. This is actually a very heterogeneous and suboptimal distribution. So, and there, of course, the seismometers were deployed on lunar regoliths, so that was not, the coupling was not good, and the sensitivity of the seismometers themselves was not good. So at the top, I show time versus amplitude for a sequence of seismographs. And all of these are derived from an area within the lunar interior, which is roughly the size of the Broad Branch campus. It's a little bit bigger than a large building. And so the advantage of lunar quakes is that they serially occur in the same spots with essentially the same wave train. So there's a sequence of seismographs at the top that all occurred at spot A6 over there. And then you can progressively stack those and get a P wave arrival, which is very faint in this, and an S wave arrival. And then you can filter these in various ways to get more information, to get interior reflections of the system. And, you know, the problem here is, of course, to find the lunar core. And this is, I believe, the most definitive word on interpreting the seismology of the lunar interior in terms of the core to date. So it indicates that a core, prior internal modeling of the density and the moment of inertia of the moon indicated that core probably exists, but the size variations were very large. And if you do a love number analysis of the associated with the tides of the moon, it looks like the moon has a molten core. And many folks have looked at lunar intrusive rocks, troctolites and so forth, that have an ancient, probably internally generated magnetic field, which in turn is also consistent with core existence. So the algorithm that a sequence of seismologists and me basically embarked on was to do a hunt and peck technique, was to basically take a sequence of possible ray paths through the lunar interior, looking at possible locations of the moon, of where the core mantle boundary might occur within the moon. There's a source here, and possible trajectories of seismic waves going up to lunar stations up here. And invert those for varying the possible location of the core, calculating the relevant travel times, and look at the seismograms to see where the actual discontinuities occur that would match various core radii. And so one can wind up with best fitting models for the S and P wave distribution, which clearly indicate that a deep core is present within the moon, and we'll look at the raw data in a second for that. And you can do travel time versus distance analyses of these for what the plausible reflection off the PCP, travel time versus distance, looks like. Now, the stations, receivers, and the balance points for this type of study, these are the red stars here are the earthquake loci. The triangles are the stations. And the crosses here, and these are the blue crosses down here, or blue triangles down here, the crosses indicate the bounce points in the lunar interior and the ray paths associated with sources to receivers. The data look horrible. They look just horrible. And what's shown here is the number of traces for different types of wave conversions or non-conversions at different interfaces within the interior. So for example, we can do a stack of compressional wave to compressional wave energy as a function of lunar radius. And we see a peak at about 250 kilometers depth in this. It's very unstable down in the deepest range because there's very few rays that access the center of the moon that are detected at the network. Get a higher amplitude near the core, get some amplitude near a possible core mantle boundary, and then there's another discontinuity that seems to persist out here. The more revealing S to P conversion, where you have shear waves going down and compressional waves coming back up, shows a relatively strong arrival at 350, 360 kilometers depth, relatively strong arrival at 230 kilometers depth, and maybe something again at 480 kilometers depth. So this is the state of the art right now, and unfortunately we have not gone back to the moon since or deployed new seismographs on the moon. We can look at other sequences of arrivals, S to S, P to S, and so forth, and get roughly comparable distances for discontinuities in the interior with a lot of noise for some of these arrivals. P to S is not very diagnostic, but there is a systematic pattern that emerges. Again, the data aren't great, but this is the best that exists. And it is all that we have to work with in essence. So what you wind up with here is because of partially the shear to p velocity conversions, you actually wind up with a relatively interesting velocity structure, in the sense that there's a major discontinuity at somewhere around 330 or 350 kilometers depth, which can be attributed to a solid liquid interface and likely a mantle core interface. It's also something that persists in many arrivals at 480 kilometers, which is within the silicate portion of the mantle and looks like it may be associated with a partial melt layer. Now, the provocative aspect of this is simply that the moon, we've long viewed it as a relatively cold body, but because it has relatively little convection that has taken place within it through time, because it is sufficiently cold in the uppermost few hundred kilometers, there's not been a lot of heat transport out of the interior. So you can actually very easily construct selenotherms through the lunar interior that result in partial melting at depth. There may also be a compositional discontinuity as well, because you'll notice the partial melt is at the bottom. And that in turn implies that there may be enrichment of transition metals within it. So we have a fluid outer core, which is something like 90 kilometers thick, and then a solid inner core, which is probably somewhere around 240 kilometers. Now, in passing, I'll mention that the amount of resolution down to this zone is quite good. Other folks, including folks in this room, Faye and others, have refined the velocities within the inner core, or proposed slightly different velocities, which makes very little difference for the structure above the outer core. Toggle these by a little bit. So the net forensics on this are that the lunar core is about 7/10 of the volume of the moon. That's consistent with its mean density of that is just slightly greater than a moon that is pure silicates, dramatically less than Earth. It seems to be overlain by a low velocity layer. And it's about 40% crystallized, so about 10 times as crystallized as Earth. So the whole picture that emerges is we've got a colder iron poor body at depth. These are the epicenters of earthquakes projected onto a single plane right there. Now, why is there this partial melt there? I'll resort to some older Japanese work where this is a sequence of density versus pressure plots for a very titanium-rich black glass as a function of temperature. So the contours here are density as a function of pressure at 4 different temperatures between 1700 and 2100 K. And the hatched area is the zone where you would anticipate that a titanium-rich melt would be neutrally buoyant. Now, you actually see these in the lunar soil. These are images of the black glass that occurs in Apollo 14 samples. And you would expect that below a depth of about 400-ish kilometers or so, depending on temperature, that melts of this composition would sink. So the notion here would be simply that there is a titania-rich layer of melt prospectively at depth within the moon. And multiple people have played with that idea since we did this. You can also construct a partial melt temperature and FES phase boundary to constrain the chemistry of the core. So if you look at a sequence of liquidus temperatures, and there's 2 axes here, one of which is the total sulfur weight percent in the core versus the sulfur weight percent in the liquid outer core. So in other words, as the inner core crystallizes, presumably the sulfur will segregate into the outer core and progressively enrich it as the inner core expands. And you see a sequence of different compositions of possible melts at depth within the moon. So green glasses would indicate that there is a relatively high lunar interior temperature and a relatively low sulfur weight content. If you actually are on the FeTiO3 clinopyroxene solidus, you'll wind up with a substantially larger weight percent, but still substantially lower than the amount of lighter alloying component in the Earth. And correspondingly, the estimated solidus of Apollo 12 picrite is over in here. So the net take here would be that the lunar core is probably sulfur depleted relative to the lighter alloying component, 10-ish weight percent in Earth's core, and that you can readily maintain a partially molten layer above the current molten core without any heroic geotherms. Lurid picture of the inside of the lunar core. That was a National Geographic picture. This raised a really bothersome issue, which is, how did the moon generate a magnetic core? My colleague Ian Garrick-Bethel at Santa Cruz has done a lot of work of the type that I described earlier, of looking at the magnetic field in lunar samples. This is a lunar troctolite from 4.3 billion years ago. And what's shown here is basically paleomagnetic results, where a cluster of circles together would indicate a coherent dipole field associated with the core. And the MCs say are medium coercivity and high coercivity. And they clearly indicate that there was what looks like it was a dipole field present at 4.3 billion years ago. Just for reference, the total magnetic field strength on the moon right now, very weak in nanotesla here. This is lunar prospector imaging. And the far side actually has substantially stronger magnetic field than the near side. Okay, so that raised the question of, which I somewhat answered before we actually did the lunar core work on, why is the moon magnetically dead when Ganymede isn't dead? And Ganymede is, of course, a slightly larger than moon-sized object that orbits Jupiter, and it is the only decent, respectable live dipole field among the moons of the solar system. It's about 3 times the field strength of Mercury, or give or take 3% that of Earth. And this is simply an image of its magnetic field interacting with the Jovian magnetosphere here. Cartoon version. Okay, so I'm going to ask the question that's directly relevant to the current liquid core of the moon. How do you generate magnetic fields in small bodies? How do they solidify? How does composition interplay with their manner of solidification? And how does that manner of solidification depend on the properties of iron-rich liquids? Turns out this is not a very simple question. And it's complicated. So many years ago, George Kennedy and Higgins, his student, proposed that the Earth might have a funny plumbing in its outer core. And the assertion that they made, incorrect by the way, was that if you had a situation where the liquidissive core material was shallower than the adiabatic gradient, the gradient that occurs on convection, then the first place that as the core cools down an adiabat, progressively marching downward through time as it cools, the first place that the liquidus is intersected, if you have an adiabat and liquidus in this relationship, is at the top of the outer core. And so you would anticipate that crystallization would proceed from the top. Of course, the scenario that, that prevails within the Earth is that the adiabat is shallower than the liquidus, and so we have the polite condition that the liquidus, actually, that the first place that the cooling adiabat, as it progresses downward in temperature, intersects the liquidus is at the center. And so the condition is that the adiabat is less than the liquidus. So the question is under what conditions do these two conditions, are there conditions under which you would expect core crystallization to proceed from the top versus from the bottom? What am I talking about here? Okay, so this picture is a very normal one, sort of a normal picture of adiabat versus melting curve, for example, for the Earth, where the inner core progressively, where the cooling core results in inner core growth through time. The counter example of the adiabat being greater than the melting curve involves essentially a snowing core. Things crystallize at the top. And the irony of that is that you both, because you're crystallizing out iron, you both enriched the outermost core of the planet in a lighter alloying component, and you release all the latent heat near the top. Both of those go fundamentally against transporting heat out of the core. So with top-down snow, or maybe it's by dendrite growth off the surface of the core mantle boundary, you get circulation that's impeded by both compositional stratification and by the effects of latent heat. In contrast, the normal core development, you actually have, you're making money here because your circulation is driven by both compositional buoyancy and by latent heat, as long as the core is on the iron-rich side of a eutectic. So it's a dramatically different scenario where this gives rise to a stably stratified core, and this gives rise to a potentially vibrantly convecting core. Now, I'm not the first to recognize that this may occur. In terms of weight percent sulfur versus melting temperature, it's been appreciated for a while. There's at low pressures, That's the approximate phase relations in the iron-sulfur system. And the end member goes up, and the eutectic goes down into lower sulfur content as you go to higher pressures. And that sulfur itself would induce, for compositions above this boundary, could induce a stably stratified system. And correspondingly, Chen and co-workers years ago recognized that within the iron-sulfur system, and this is a sequence of synthetic possible adiabats within a core, and the temperature inferred for different sulfur weight percent for the melting relations within the outer core, that you could get very complicated behavior where in portions the adiabat is shallower than the melting curve, in other places where it's steeper, and get a very, very complicated picture taking place. And this goes up to roughly 40 GPa, whereas the center of the moon is roughly 5 GPa. So what I did was a pretty standard thermodynamic analysis here. I basically calculated what the adiabat was as a function of pressure and temperature, and calculated density for iron and iron alloys using bulk moduli of liquid iron and its alloys. I'll return to how these bulk moduli are determined in just a little bit, because there's more insight that can be garnered into interiors of planets than simply the relation between the adiabat and the melting curve. So if you just look at the formula for the adiabat, it's the thermal expansion, which is a function of pressure and temperature, times the density as a function of pressure, times the heat capacity. Heat capacity is pretty monotonous, and it's really pretty easy to figure out what it is for modest pressure conditions with an iron alloyed compounds. There's really a weird relationship with thermal expansion. So I've plotted here every thermal piece of density as a function of temperature data that I could on end member iron. And there are something like 10 or 12 studies embedded on here. And loosely, most of them scatter around a fairly robust line that is outlined by the purple and red points and by the dark line here. For one reason or another, and I can explain the sociology of this, and it really is sociological, I believe. For many years, the thermal expansion of liquid iron that has been used in the planetary sciences literature has been on this green line. And the reason for that partially is that there were a sequence of measurements of gamma ray attenuation of thermal expansion of iron that yielded a relatively low value. These are really hard measurements. And essentially everyone else who used Archimedean, picnometric, bubble pressure, levitated drop, heated wire, all came out with values that were somewhere on a line like this. This isn't a subtle difference, as it turns out, and as I'll show in a second, because the difference in thermal expansion between this and that, if I take the derivative of those two, is a difference of almost 50%. So the difference is that this is basically 8 times 10 to the minus 5 versus 13 times 10 to the minus 5, a little over 50%. Just to remind you of the iron phase diagram, and this is work done at General Electric many years ago. You have a almost linear melting curve for iron in the body-centered cubic structure up until about 5 GPa, which is actually almost exactly the interior pressure of the moon. And then, of course, there's the well-known alpha to gamma transition. And the nice thing is that we don't actually have to worry too much about this peculiar field up here, because as you add sulfur and nickel to this system, this field markedly contracts. So for most planetary cores, it's not particularly relevant. Okay, so this is a very busy plot, which I will walk through fairly carefully because it's the crux of this story, which is, if I were to just make a core out of pure iron liquid, and I looked at the melting curve of iron. This is the fairly linear melting curve of iron I showed you on the previous overhead, about 35 K per GPa. Takes a little bit of a jump in accord with Schreinermacher's rule at the triple point here. And what I've done here is calculate a sequence of adiabats as a function of pressure. And so where the adiabats, which will decrease as a function of pressure because thermal expansion will decrease as a function of pressure. And I use a couple of different models for how the thermal expansion will decrease with pressure. That if you look, what's shown by these red lines is using a liquid iron adiabat calculated for high values of the thermal expansion 13.2 times 10 to the minus 5, and for different values of the pressure derivative of the bulk modulus. So relatively low values up here, relatively high values down here. I'm going to return to this pressure derivative of the bulk modulus at the end of the talk with some more recent work. Now, so clearly, once you get into the interior of Ganymede, the lunar center, if you have these high values for the melting curve of iron, you are in, even for a pure iron core, you're in a mode where the adiabat is steeper than the melting curve. If, on the other hand, the thermal expansion is lower, and this is where this number really matters, you wind up with substantially lower values for the adiabat. And this is a normal core. We'll call it a core that crystallizes from the center out. So right now we have a fundamental dichotomy which hinges dramatically on the thermal expansion of molten iron and its pressure dependence and its pressure derivative of the bulk modulus. Effectively, whether cores of smaller bodies, whether it's Vesta, Callisto, the Moon, Ganymede, convect from the top down or from the bottom up hinges on second order thermodynamic parameters. That's horrifying. Actually, I'm kind of horrified by that personally, because it's a major change in dynamics dictated by some rather secondary phenomena. So that has disturbing aspects. And of course, if you look at the role of nickel and sulfur on the system, if anything, nickel may cause a little bit of reduction in the thermal expansion, a little bit, but you have to put in a lot of nickel before anything happens. And sulfur, there's relatively few data points, but it seems to push the thermal expansion way the heck up. So if I add a little bit of nickel at the sort of cosmic chemical level, 5 or 10%, and add, a few weight percent of sulfur, I would basically expect the thermal expansion to remain roughly constant. Do we know that? No. That's an area where experiments have to be done. If we put in a little bit of sulfur, then the result actually shifts in the favor of having stably stratified cores. So here are adiabats for both 5 weight percent, those are the dotted lines, and red lines are 10 weight percent sulfur, so sort of spanning a Earth-like range, or I would call this a moon-like range of sulfur contents versus a Earth-like range of possible sulfur contents. And the liquidi slope for sulfur-rich compositions lies about right here. So the two dotted lines at these two different thermal expansions lie above at most conditions, and correspondingly the 10 weight percent lies above the 10 weight percent liquidi at all conditions. So the bottom line here is that the cores of small bodies don't really behave like the core of Earth. They look like they crystallize from the top down. The only exceptions I can really come up with are very sulfur-poor objects, which in some instances that are in Ganymede-sized or larger objects could actually crystallize from the bottom up. And that bodies with present magnetic fields might have sulfur-rich cores, or they might generate their fields from fluid motion in a fairly limited depth range. That presents its own set of problems with how their dynamo works. And the bodies with ancient fields, and that would be the Moon and the Angrite parent body, which seems to have had an ancient field, could have generated their fields maybe in a fully molten core regime with high heat flow, because there's no way that the Moon right now looks like it could generate a magnetic field, given that it is almost certainly stably stratified at depth. And so that stable stratification is probably the state right now of the lunar moon. And it's probably crystallizing via an iron snow regime. And the point that I'll raise in this part of the talk is that these large alpha values, which really we don't know very much about how their pressure dependence varies. And that's a key area moving forward in my mind for refining the thermodynamic properties of iron-rich liquids. But those fundamentally govern the dynamics and hence the magnetic field generation in small planetary bodies. Now, I mentioned a while ago that the pressure derivatives of the bulk modulus, I bounced them around between 4.66 or something like that for iron liquid and something much larger. Why did I do that? So I want to pose whether there's other derivative parameters that are critical for determining the density of iron-rich liquids at core conditions. And the answer is yes. and I'll foreshadow that by just saying that the pressure dependence of the bulk modulus turns out to be critically important. And there's been a huge amount of work, and lots of people in this room have worked on it, so I'm not going to give a comprehensive overview of every piece of work on possible core composition from elasticity of core liquids. But ultimately, there's relatively little leverage we have in terms of data that can actually constrain the lighter alloying component of Earth's core. There's basically the sound velocity, which in turn is dependent, and we have a decent idea of the density, reasonable, not great, as a function of depth. And the combination of those two leads us to the bulk modulus and its depth dependence or pressure dependence, which in turn gives us the pressure dependence of the bulk modulus as well. So the ambient pressure, I'll just make the assertion right now, and I'll show you in a second why this is important, that the ambient pressure, high temperature elasticity of melts really provides a critical fixed point for the bulk modulus. And you can then deploy high pressure measurements to constrain the pressure derivative of the bulk modulus. What I'm going to talk about is ultrasonic or interferometry that I did in collaboration with some Hawaii folks, published a year or two ago, to measure sound velocities at high temperatures. We particularly picked iron, nickel, silicon liquids for a reason which I'll show you in a moment, which is that there's a lot of complementary data that exists that we could actually deploy to actually figure out what the elasticity of these liquids are. So just to remind you, if you're a geochemist or just someone who doesn't eat bulk moduli for breakfast, that the bulk moduli is, of course, the change in, is 1 over the compressibility. It is the change in volume as a function of, it reflects the change in volume as a function of pressure. And in turn, if we look at the standard Prem velocity model, so with this being liquid, this is equal to the square root of the bulk modulus divided by the density, that the slope of this line is controlled by the combination of the pressure dependence of the bulk modulus and the shift in density itself, which is in turn a function of the bulk modulus as well. And in most geophysical solids, this is a really pretty monotonous and tiresome parameter. It's unitless, as you will have detected, because this is the bulk modulus. dkdp is unitless. It usually varies between about 4 and 5.5, give or take a little bit. But its value within geophysical liquids is a lot less well constrained. And in particular, I would also point out that silicon melts are also reasonably well constrained, reasonably poorly constrained in terms of their bulk derivative of bulk moduli value. And I'll just note that, of course, you can do, since this is thermodynamics, you can do this in both adiabatic and isothermal flavors, and that will come in as an important ancillary point in a few minutes. So this is the standard ultrasonic measuring setup, which basically involves a pair of buffer rods, melt in between them, and heating the material up, propagating a ultrasonic wave through the system, and looking at its amplitude as a function of melt thickness, where you get, at a given frequency, you get destructive and constructive interference. And you can also modulate the frequency of this to see if there is a frequency-dependent effect that reflects an attenuation of the liquid as well. So it's a relatively straightforward analysis that actually is very robust and extremely accurate. And if we look at the temperature dependence of a sequence of silicon-rich melts, or iron, nickel, silicon alloys, you can see that there's and the length of these lines is governed by the initial melting temperature. Stuff with more lighter alloying elements melts lower. But basically, we get a pretty good handle on the temperature derivatives of these as a function of compressional velocity. And we have a decent thermal window on what exactly the temperature interval over which these velocity changes take place. Temperature derivatives, we can calculate them for this, and they're a little bit lower than that of iron under the same circumstances. If we look at the, and those should show up stronger, but that's at p-wave velocity as a function of composition, a pretty monotonic trend in terms of sound velocity. And that's not surprising because the addition of silicon lowers the density of the melt as a first order effect. Eventually, we expect this to turn over and come back down. You'll notice that silicon actually, end-member silicon actually has an inverted, positive temperature slope of the compressional wave velocity. So this is not surprising. And since we know the densities are very well constrained, that the density as a function of weight percent was constrained years ago by, in France, and we have a fairly accurate constraint on what the densities of these liquids are, and hence we can, we can invert for bulk modulus as well. So we have the adiabatic bulk modulus as a function of weight percent silicon, and we have an excellent handle on how, for a given weight percent silicon, how much the system softens. All right, well, there's actually a lot of complementary data, which is why we deployed the iron nickel silicon system. There's a bunch of different measurements of compositions which mirror exactly ones that we worked on here, which are, there are X-ray absorption studies outlined that were done in France last decade that are outlined here. There have been sink float measurements, which we do not understand the discrepancy with up here. And there have been another sequence of sink float measurements, which actually we can fit fairly closely with isothermal bulk moduli. And these would be isothermal because these are actually looking at the properties of iron silicon liquids under isothermal circumstances, which we can fit fairly well with the upper curve here is a K prime of 4, the lower one is a K prime of 8. And typically with a little bit of difference down here, we can fit fairly well with a relatively high K prime with the former sink float measurements of U and SECO. Okay, so it's not really a very clean picture, but at least there's one data set that if we look at the right density and we look at the correct bulk modulus that we infer, we can get reasonable match. Now, the relationship between the isothermal bulk modulus and the isentropic bulk modulus is up here. I'm not going to belabor it too much except to say that that same uncertainty that dogs thermal expansion that I talked about in the previous part of the talk also dogs this conversion from Ks to Kt. So again, what we're seeing here with these two different values of the bulk modulus is a correction of our adiabatic values to isothermal values using two different values of the thermal expansion. And the ugliness I refer to here is simply refers back to this horrible plot, which I won't bother you with again. Okay. There actually is a higher pressure data set too. This is incredibly challenging work that was done by the French group of Morard et al. And EPSL, published a few years back. And what they did was they looked at the X-ray diffuse scattering of these liquids at a broad range of conditions. So the silicon points are in blue over here, and they span from something like 27 GPa on up to 80 GPa or so. And they inverted these, and they actually did not have a great constraint on what the zero pressure density was, which one would think that if you're doing all this work to get out the high pressure density, that the zero pressure density would be well constrained, but they fit these data and wound up with a relatively high value for the zero pressure density of this material. The stark results are that the numbers that they got are wildly discrepant with the ultrasonic data, wildly discrepant. By that, I mean they're at higher temperature, so probably the liquid should be softer at higher temperature. And they were getting bulk moduli that they inverted for with a K prime of 4 of 200 GPa for their data out over here. And just for reference, our results 1,000 K lower came up with a isothermal values for this that are essentially either a third, if I like high values of the thermal expansion, or half their values for the low thermal expansion. Is this a problem? No, it's an advantage. This is wonderful. This is the best thing ever. Why is it the best thing ever? Because once we incorporate a thermal correction to the bulk modulus, and we compare it directly with X-ray measurements that they did at right around 2,850 K, and these are their data dramatically blown up, we can play all sorts of fit games with them, especially if we use good values for the zero pressure density, which one should, in general, not use high pressure liquid density to extrapolate back to zero density. That would be one lesson I would take out of this. What you get are basically, you can fit these data pretty nicely, actually, with very low isothermal bulk moduli. So what I'm saying here is, actually these bulk moduli, they actually don't matter for the core. We don't care what the bulk modulus is. It might as well be 0. What we care about is actually the pressure derivative of the bulk modulus, because that's all that matters. I mean, you can multiply 10 by 40 and get what the difference in elasticity is for squeezing on something to 40 GPa from K prime times dP, and you'll get something like 400, give or take. And your initial bulk modulus is probably an order of magnitude less. So ultimately, the combination of the sink float measurements, which I have not shown here, but came up with a K prime of around 8, and the higher pressure X-ray diffuse scattering measurements all sum up to a collective pressure derivative of the bulk modulus. It's very high by standards. Remember I said that this was something like 4 to 5.5 for most solids? In this instance, it looks more like it's 10. 9 to 12.5 would be sort of my preferred range for this. So the key aspect here is that because there are many probes that are available for the density of these particular liquids at a wide suite of pressures, and we can tie them in very accurately to very robust measurements at ambient pressure, we can infer what the entire equation of state of the liquid is up to very high pressures, up to pressures that approach those of the core mantle boundary. Okay, why does this matter? Oh, this is just to amplify the effect of ambient pressure density here. That if, for example, you're looking at FESI liquid densities at 1700 K, and you actually do a thermal correction on it of 1000 K for things like the Morard data, you get a density which is dramatically lowered, which rationalizes why we can basically put our lower pressure data point. Notice that they, on this FESI liquid density plot, for this composition, they chose a value which was near 6, which is very good for the FESI liquid density at 1723. I would put it somewhere down here. And that's also where the dramatic curvature of this system comes in as well, is that you also need to do, unsurprisingly, this should come as a shock to no one, you really should know the zero pressure volume of a material before you do high pressure elasticity. It's just one of the little rules that we should obey. Okay, so if I actually extrapolate this, wildly as inevitably one has to do when one has elasticity data on a iron-rich liquid, you have to wildly extrapolate it out to the outer core and preferably into the inner core range. What one gets from these different values for the elasticity vary quite markedly. So for example, the previous Morard fit actually wound up with a relatively high density for this type of composition for for the isothermal compressibility of this liquid. It wound up at a little bit over 10. For these much lower bulk moduli and much higher K primes, you actually wind up with a substantially depressed density for iron silicon liquids at core and inner core, at core and top of the inner core conditions. So it actually turns out that this type of difference in slope actually really matters for what we infer for the core composition. And in particular, if we just compare the equation of state of iron, nickel, 15 weight percent silicon liquid at 2850 K, these are isotherms here, with the plausible range present. I've put on the preliminary reference Earth model right here, and then plotted up a sequence of solid data on here as well, which actually looks like it mirrors Prem fairly nicely. The thing I would emphasize is that this is an isotherm now. So if you make this an adiabatic curve so that the temperature increases as a function of depth, this will steepen this up. And the mismatch with the seismically observed velocity distribution within the core will become substantially larger. So, and I put up some relevant shock data here as well, which I think Faye was a co-author on this particular work as well. So the key aspect here is that you wind up having a divergence. If you put in a lot of silicon into the outer core, you have to essentially mix something in that will bring it back, that will unsteepen it to bring it back to a Prem value. And that's why I put on this figure over here of looking at what the relative slopes of oxygen and sulfur are for shock-loaded material, to say that there isn't a component that is going to drag these curves the other way to compensate for the stiffness of the silicon content of the outer core. So I'll conclude here. So the reason we picked iron, nickel, silicon in this particular instance is we knew there was a lot of data. There was a lot of actually quite discrepant data out there. But as it turned out, the combination of really good low P elasticity combined with high P sink float data and X-ray diffuse scattering all provide a very nice constraint on on FESI liquids. And essentially they require high pressure derivatives of the bulk modulus for these liquids. And I'll make an ancillary comment for those that are very technically inclined, of which I know there are a few in the room, which is that unlike many materials, everyone blurs their eyes and says, if you have an adiabatic pressure derivative of the bulk modulus and you have an isothermal pressure derivative of the bulk modulus, they're about the same. In fact, the relationship is reasonably complex and depends a lot on the thermal expansion, also on the temperature as well. So actually, isothermal K primes of 8 to 12 map into adiabatic K primes that are substantially less. And that's an effect which I'm playing with right now, actually, is looking at the relative interplay between those. Key point that I would emphasize here, and this is just for one possible component of the outer core where, of course, you know, the garden variety list runs sulfur, oxygen, silicon, maybe carbon, maybe hydrogen. But we're nowhere, I would argue, in terms of understanding the detailed equations of state of these materials. That the equations of state at the level that we need to actually know what the elasticity of the outer core can be as a function of different lighter alloying components, that the data set is not there, and that it all hinges on basically accurate values of K prime. I think this is actually an area where mineral physics will, over the next few years, will actually ultimately converge on enough different probes of the panoply of iron-bearing rich systems, sulfur, oxygen, silicon, when we have silicon done, sulfur, oxygen, carbon, and so forth, that we will ultimately be able to evolve accurate K primes because those are really the numbers that matter for the outer core composition. And I'll just say that the elastic properties of iron silicon liquids make it hard to put a lot of silicon in the core. It really is very difficult. You can play with the numbers in great detail on this. But silicon as even a minor core component. By minor, I don't mean minor like trace elements and things like that. But if you stick in more than a couple weight percent, it's really hard to match the density distribution of Prem. In fact, I would argue, based on what we know right now, it's essentially impossible. So I would put, you know, with the outer core being the iron-rich garbage can of the planet, I'd say you want to put a percent there, you want to put a 1.5%, fine, you can do it. But you don't want to make it very abundant because it's going to be very hard to match the properties of the outer core. And then I would just say that meaningful constraints on core liquids really require a multi-pronged experimental approach. And that my emphasis would be that, you know, there's been a focus over the years on the primacy of the bulk modulus. If you know the bulk modulus, you know so much about a material. I would actually argue if you know the bulk modulus of many liquids, you know nothing about the material. You know very, very little. It's an almost useless parameter for the interior of the planet. What you need to know is you need to know things like K prime. Because, let's face it, interior of the planet's at a big pressure, and if you have big values of dKdP, you wind up with a dominant influence on the bulk modulus of the interior. And so the multi-pronged experimental approach really, really matters. And that's something where a intergroup approach and a cross and potentially even a cross-institutional approach in a place like the Geophysical Lab might ultimately solve this dreadful problem of core composition, which has dogged people since actually even prior to 1952 and Francis Birch. It was recognized that the core was problematic. So I'll stop there. Thanks very much. I agree with you. I mean, I will say, as you know well, that there are always little issues with dynamic pressure measurements. And they come with their own set of difficulties in a sense. So I will freely grant you that shockwave measurements may well provide a locus of solutions down the line, and that they are of key importance. But their irritating aspect of tracking similar PT paths, although you can do clever things with samples, does provide a limitation to them as well. So they are one component, certainly, of the entire story, and you're correct on that. Mm-hmm. Right. Right. But the key aspect is the trade-off between K and K prime is always a dilemma, in a sense, with even shockwave data, in a sense. So if you have something to tie into, and that's kind of a key message here. If you can tie into something at ambient pressure, do the temperature correction on up to along the Hugonia or along the release path, then you're in good shape. But I would argue that if you solely look at the high pressure portion of the shock results, you may not fully get, there are many possible trade-offs between K and K prime that one can evaluate. So I agree with your sentiment, but I would insert a cautionary note behind it, which you're pretty honest in your papers, I'll say that. Right. 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 Yeah. Mm-hmm. Mm-hmm. Right. Yep. Yeah. I so emphatically agree with you, I cannot even express myself in terms of my emphatic agreement. I am waxing ecstatic, yes. I agree with you. And I mean, certainly, yes, there are, as I say, there are always, shock measurements are always, have some challenges associated with them that are separate from this, and I'm sure you can give an entire talk on that as well. Mm-hmm. Certainly at low pressures, there's no question, I think, that they would go into the liquid. So, and I would argue that that probably persists to high pressures as well. So in other words, the iron-rich stuff precipitates out, leaves behind whatever lighter alloying component in a top-down configuration. So that would be my, and I think that the argument is robust for low pressure, is completely robust for low pressure conditions, probably pretty good for high pressure conditions as well. This is, okay, there's a very complicated issue you're raising, which is whether the entire core, as it cools, ultimately converges on the liquidus, so that, because the key question that, I'll add a question to your question, which is, if in fact this is a situation where the core is crystallizing from the top down, at least initially you would expect that as the crystals descend, they might redissolve. Then how do you get an inner core? And the only way to get an inner core is basically to pin the entire core to the liquidus, the entire outer core to the liquidus. That's really the only way to do it. So that would stabilize material all along the descent path of the snow. Now, there's a supplementary question embedded in that as well of what is the detailed, what does this, I called it snowing because a lot of people have called it snowing. That might be wrong. In fact, I would occasionally say that it might be descending iron daggers from the top of the outer core. And that, if you crystallize iron-rich melts at a range of conditions, especially slowly, you get dendrites. And it's very well documented that you get dendritic behavior of these. So, and in some asteroids, some asteroidal interiors, there has been the argument, people at Hawaii among others, that you actually see indications in some iron-rich meteorites of dendrites that could be kilometer-length scale, which is a startling statement in my own mind. So if in fact you have dendrites that, oh, one thing to keep in mind here, let's approximate the gravity here in many of these smaller bodies, let's say an angrite parent body or Vesta, let's approximate the gravity as 0 because they have almost no gravity. You know, their gravity is a tiny, tiny 0.02 meters per second squared or something like that. It's because they're small bodies. So you could actually envision a scenario where you actually have large dendrites descending downward, and that eventually, depending on the adhesion with the overlying core mantle boundary, eventually decide to descend and can then basically, depending on the dissolution rate of the dendrites, and now we are approaching planetary science fantasy, depending on the dissolution rate of the dendrites, actually wind up descending to the inner core and forming a core-like body at depth. So that's a scenario which I can't preclude. I actually kind of prefer, I mean, everyone has used this iron snow thing, and I'm actually not overly fond of it, I have to say. I prefer the iron daggers of death. So, did that answer your question? Okay. Mm-hmm. Okay. Yeah, I think the most vital one is that I think, for better or worse, that the inversion, I will say this, that inverting the X-ray diffuse scattering data for a density is not a simple process in what is ultimately a laser-heated multi-phase sample. It's not simple, it's not straightforward, and so, for example, with the Morard data, do I swear on a stack of Bibles that that's right? I don't know. It may well be. It is the isothermal data that is out there right now. So I do think that the net technical steps forward will be to improve the capabilities of doing, for better or worse, probing it with X-rays, because I don't know another way to do the density of an iron-rich liquid, you know, other than shock measurement, but to modulate the temperature widely and the pressure widely. I mean, you are constrained in shock wave measurements to certain PT paths. And so to relax this shock constraint, it will require that a substantially better and more well-developed set of procedures is launched for the for analyzing X-ray diffuse scattering of liquids, which could be applied broadly. And I know that folks who in the room have worried about that quite a bit. And I will say that my own view is that the Morard data is probably heroic. I mean, that's a heroic stunt in my view. It was a very hard set of measurements. They had to do lots of corrections. It's not a simple, you look at it and you think, God, I hope this is right. That's what you can say, I think. And so I think that is going to be, whether you're thinking about silicates or iron-rich liquids, that is the interface of, like, for example, what is the temperature dependence and the pressure dependence, you know, at 50, 80 GPa. It's important for mag motions for silicate liquids. It's important for to even extend the pressure range as well, and that's a trick. And there may be technical expertise in this room that can do X-ray diffuse scattering on a liquid at 150 GPa and 3,500 K. Dave? Dave? Volunteering? It's hard. I mean, there's no question about it. I think that's a very challenging measurement to make, no matter how you cut it. Mm-hmm. That's right. Right. Yeah, that's right. That's right. Right. Exactly. And I mean, the reason I chose to talk about this today was simply that, you know, I mean, I can talk about volatiles and their exotic behaviors at high P&T and so forth. But I felt this is something where certainly the GL has played a primary role in the past, and the challenges are mushrooming as a function of time. It's not getting any easier, unfortunately. The solution has not been derived, I don't think, and that this is an area that I think